Probability is a measure of uncertainty. In this lecture, we will discuss the development of mathematical probability in history. We'll look at some rules and laws that must be understood to understand probability, and we'll look at some applications of probability on our everyday lives. The idea of uncertainty was definitely known to ancient peoples. We have records from soothsayers who rolled the knuckle bones of dogs much as we roll dice today. And those records indicate from the results required to have certain outcomes that these people understood about probability. But the notion of probability still was not really worked upon mathematically, probably until the late 15th century. People at that point in time, well, certain people began to recognize that results of gambling situations were not simply random in terms of something that you couldn't predict, but indeed there were mathematical truths involved in the outcomes of gaming situations. The first we know about occurred in 1494. Luca Pacioli, who was an Italian mathematician and wrote about games of chance. And he really didn't identify specific rules of probability, but that was the beginning. Later, during the 16th century, Girolamo Cardano, who we've mentioned before and who did a great deal of work in mathematics, studied gambling. And he did this for a very good reason. He had a mathematical degree. He also had a medical degree. But unfortunately, he had been born out of wedlock. So when he graduated from the local university, he could not obtain a job. And he began gambling. He used his great intelligence and his mathematical knowledge to win. And of course, he only wrote his book about gambling and the mathematics involved after he was quite wealthy. And he published his findings and went on to become a professor of mathematics and, in fact, the physician to the Doge, who was the local duke of the city-state where Cardano lived. His life went downhill from there, actually. The fact is that his wife left him for another man. His only son was convicted of treason and executed. And the ultimate disaster was that Cardano became quite egocentric and predicted the date of his death. When that day arrived and he wasn't sick, didn't appear to be dying, he committed suicide. So the man was a bit strange, but he actually laid the groundwork for modern probability. And for that reason, we have to hold him in high regard. Later, during the 17th century, Blaise Pascal, who you've seen already for Pascal's triangle, and Pierre de Fermat, two French mathematicians and philosophers, conducted an exchange of correspondence dealing with the outcomes of the rolls of dice. And they were actually applying mathematics to a situation which still many people thought were totally random with no rules for expectation. Finally, in 1718, Abraham de Moivre, a French mathematician whose name has been mentioned in previous lectures, wrote a text called Doctrine of Chance, in which he investigated the theory of probability. Probability was becoming a branch of mathematics, which today it is. Later in that century, G.L. Leclerc, who was the Comte du Buffon, flipped a coin 4,040 times and recorded 2,048 heads. There are two questions one must ask. First of all, did he have nothing better to do? And more importantly, why 4,040? Was that a magic number? I have no idea, but the recording of that result for so many flips indicated that it appeared that the probability of getting a head on the coin that the Count used was 0.5069. Buffon's experiment was the first of many attempts to validate what's called the law of large numbers. This law states that if you repeat an event enough times, the result should match the theoretical result. The theoretical result of flipping a coin, a fair coin, is that you should get heads about half the time. Little was done in terms of scientific investigation of probability until the 20th century. At the beginning of the century, Carl Pearson, one of the fathers of statistics, repeated Buffon's experiment, but he flipped a coin 24,000 times. He really had very little to do. And he counted 12,012 heads, which gives us a probability of 0.5005, quite close to the theoretical probability of 0.5. John Kerridge, An Australian was imprisoned by the Germans during World War II. And he used his time of incarceration to do a coin flipping experiment. He flipped a coin 10,000 times. Unlike the previous two gentlemen, at least we knew that Kerridge truly had nothing much else to do, and he devoted his time as a prisoner of war to doing a scientific experiment. He obtained 5,067 heads, which would give you a probability of 0.5067. The expanding need in the area of insurance during the 20th century required a scientific study of the results of chance so that insurance companies could make accurate predictions of their losses and therefore make accurate predictions of what premiums should be required. This led to what's called actuarial science. Actuaries actually work for insurance companies and determine the probability of various events. A certain type of person dying, a certain house burning down, etc. As businesses grew throughout the 20th century, the operation of major businesses became more complex, and there was an increasing need to quantify chance. And the chance of success, obviously in business, is something you really need to know. Is the business going to be profitable or not? And therefore, various strategies had to be looked at and evaluated in terms of success. From this need came a branch of mathematics called game theory. Game theory basically is a probabilistic treatment of a win-lose situation. Either the business is successful or it is not successful. Since probability is a branch of mathematics, some basic definitions and fundamental rules must be established. Probability is a measure of uncertainty. There are two types of certainty. One is a situation where you are certain something will happen. For example, if I roll a fair die, typical die that has 6 faces on it, I know that when it lands and that one face is up, that face will have less than 7 dots on it. Also, there's the certainty situation where you have a certainty that you know it will not happen. For example, I flip a fair American quarter and it lands with one face up. I know there is no chance that face will be a picture of George III of England. So basically, we have these two types of certainties. I'm certain it will not happen, which is a probability of 0, and I'm certain it will happen, which is a probability of 1. Since all degrees of uncertainty lie between those two, the probability for an uncertain situation will be between 0 and 1. That is, it will be a proper fraction. If all possible outcomes are equally likely, the probability of a particular result will be the ratio of the number of outcomes that will give that result over the total number of outcomes. Let's look at an example we've talked about in a previous lecture. That is flipping 3 coins, a penny, a nickel, and a dime. If we do this, we have a table, which you can see, that shows us the possible outcomes for the flips. And we can either get a head or a tail on any of the coins. So you'll notice there are exactly 8 possible outcomes. And since each outcome is equally likely, we assume that the probabilities of each will be 1 out of 8. The results of 2 heads occurring happens in 3 of the outcomes: the head, head, tail, the head, tail, head, and the tail, head, head. And therefore, the probability of flipping 3 fair coins and obtaining exactly 2 heads, and therefore also 1 tail, is 3 out of 8, 3/8, or 37.5%. Since there is certainty that one of the results, either 0, 1, 2, or 3 heads, will occur, we know that the probability or the sum of the probabilities must be 1. And therefore, we can look at the probabilities, the probability of 0, plus the probability of 1, plus the probability of 2, and plus the probability of 3. And using our table, we get 1/8 for the probability of 0, 3/8 for the probability of 1. We already have seen why 3/8 is the probability of 2, and 1/8 for the probability of getting 3 heads. And when you sum those 4 fractions up, you get 8/8, which is 1. Indeed, the theory appears to be quite correct. Let's take a look at the 3 basic rules of probability. Those rules involve an and situation, or situation, and a not situation. For example, let's take a look at a probability situation involving a standard deck of 52 cards, 52 playing cards. We look at the probability of one event happening or another. For example, what is the probability of selecting at random from a well-shuffled deck a face card or a 7? In other words, let's say you were playing a game, and to win the game you had to draw one card, and it had to be a face card, a jack, a queen, or a king, or a 7. Well, we know that the probability of picking a face card is 12 out of 52. There are 12 face cards out of the 52 cards in the deck. And the probability of picking a 7 is 4 out of 52, since there are 4 cards in the deck that are 7s. Therefore, the total probability would be 16. It appears that the or situation is additive. But if we were seeking to find the probability of a face card or a heart, we might have a little problem if we simply added the two probabilities, because the probability of a face card is still 12 out of 52. The probability of a heart is 13 out of 52, which would tend to make us believe the probability was 25 out of 52, but there is one problem. There are 3 face cards that are also hearts. We have double counted the jack, the queen, and the king of hearts, and therefore we need to subtract any double counting, which leads us to the general formula or rule for the probability of an or situation. The probability of A or B, where A and B are 2 separate events, such as picking a face card and B might be picking a heart, is equal to the probability of A plus the probability of B minus the probability of A and B, or minus the probability of both. And therefore that would be a 12/15 plus 12/52 plus 13/52 minus the 3/52. That would be the probability of picking a card that was both a heart and a face card. And therefore that would give us a probability overall of 22/52. So if the game involved picking a card from a well-shuffled deck, and you would win the game if you picked a face card or a heart, your chance of winning, in general, would be 22 chances out of 52. Okay. The idea that something can not occur simultaneously with something else, that is, the probability of A and B is 0, that is called mutually exclusive events, or sometimes it's called disjoint events. And when you have that, obviously, as we did in the probability of picking a face card or a 7, the subtractive part, the probability of A and B, is 0. If 2 events have no effect on each other, that is, knowing something about one event does not change the probability of the second event, those 2 events are called independent. A good example of independence would be that I would assume that whether or not it rains in Spokane, Washington, has very little to do with the New York Yankees winning a home game at Yankee Stadium. And therefore, since one does not affect the other, nor does the idea that whether the Yankees win or lose at Yankee Stadium affect the weather in Spokane, Washington, therefore those 2 events are independent. Now, for example, if a child studies for a test, we would not say that that event is independent of the child's grade on the test. We would assume that the more the child studied up to some point, the better the grade would be, and therefore those 2 events, studying on a test and the result of a test, are not independent. And we would say that something is independent if the probability of A equals the probability of A given B. Notice the symbology. It has P of A equals P of A, and is a vertical line segment, B. That vertical line segment means if, or given. And therefore, the probability of A, given that B has occurred, if that's equal to the probability of A, then we have 2 events, A and B, which are independent. Again, going back to our example, the probability of the Yankees winning a home game is equal to the probability of the Yankees winning a home game if it rains in Spokane. We're assuming they're independent, and that's how we would define that. Now, independence is quite important when we're dealing with the second situation, which is the and situation. Because the probability of A and B, if 2 events are independent, is simply the product of those 2 probabilities. So, for example, the product the probability of, on one given day, it raining in Spokane, Washington, and the Yankees winning a home game is equal to the probability of rain in general in Spokane times the probability of the Yankees winning a home game at Yankee Stadium. We multiply because those two events are independent. What if the events are not independent? Then we have a general formula, which we'll look at now. And that says that the probability of A and B, that is the probability of both events occurring at the same time, is equal to the probability of A times the probability of B if A occurs. Now notice that second probability is equal to the probability of B if the two events are independent. But if they're not independent, then we must know that probability, the probability of B if A. And therefore we can figure out what the overall probability is. One thing I should mention at this point is that you'll notice we add in one situation and we multiply in the other situation. And the question comes about, how do I know whether I'm adding or multiplying? Well, that is quite simple when you reflect upon our arithmetic of fractions. When you add two fractions, you get a bigger fraction. 1/2 plus 1/4 is 3/4. On the other hand, when you multiply two fractions, you get a smaller fraction. 1/2 times 1/4 is 1/8. The probability of AND must always be smaller than the individual probabilities. Why is that? Well, take a situation. Let's say you were applying for a job, and that job existed in one of two companies, and those two companies were identical in every way except their requirements. One company required you to have a college degree or 2 years experience in the field. The other company required you to have a college degree and 2 years experience in the field. In which company would you have a greater chance in general of getting a job? Well, obviously, if you only had a college degree and did not have the experience, or you only had the experience but without the degree, you would get hired in company A, but you would not in company B. So OR has a greater probability than and therefore OR goes with addition, and goes with multiplication. The third type of probability rule has to do with not. A question I like to ask my students is, if the probability of rain today is 30%, what's the probability of it being sunny? And in unison they say 70%, because 100% minus 30% is 70%. Now, that's wrong. The probability, that is, if the probability of rain is 30%, the probability of it not raining is 70%. Not raining could be cloudy, and it could be sunny, and it could be raining. So the idea is we deal with a situation and not that situation. And those are called complementary events. And since those two events are the only possibilities, either it's raining or it's not. Either you win or you don't. The sum of those two probabilities must be 1. That is, the probability of A plus the probability of not A must equal 1. And therefore, the probability of not A is equal to 1 minus the probability of A. Let's look at an example that might demonstrate these three rules. A customer enters a store that sells both books and music. We have quite a few of those in our major cities, and even in almost any suburban mall you'll find a store that sells both books and music. And she has a 1/4 chance of purchasing a book that day, and she has a 2/5 chance of purchasing a CD that day. And the two events, purchasing a book and purchasing a CD, are independent. The question that must be asked by the store manager as the lady walks in is, what is the probability that she will buy neither a book nor a CD? Since the event buying nothing, symbolically the probability of 0, is the complement of buying something, the probability we seek is written as 1 minus the probability of B or CD, where B stands for buying a book and CD stands for buying a CD. Now we use our formulas. Notice that the next line says the probability of 0 is 1 minus, and we've had a bracket, the probability of B plus the probability of CD minus the probability of B and CD. We have used the rule for AND, the addition rule, that the probability of A or B, in this case B or CD, is equal to the probability of the first plus the probability of the second minus the probability of both occurring. Now, since the events, buying a book and buying a CD, are independent, we can simply multiply those two probabilities to get the probability of both occurring. So again, our formula reads, the probability of 0 is 1 minus bracket the probability of B plus the probability of CD minus the probability of B times the probability of CD. Since this is an arithmetic problem, once we plug numbers in, we are going to multiply before we subtract or add. And then after we get one number inside the brackets, we will subtract that number from 1. So let's go ahead and do the arithmetic. We have the probability of 0 is equal to 1 minus 1/4. Remember that is the probability that she will buy a book, plus 2/5, the probability that she will purchase a CD, minus 1/4 times 2/5. And we multiply and subtract and add. We get 1 minus 11/20, which gives us a probability of 9/20, or 45%. So there's a 45% chance that this woman walking into the store on this day will buy nothing, which means there's a 55% chance that she'll buy something. Now, if you're looking at the numbers involved, you might say, wait a second, I think I see an easier way to do this. If we simply take the probability of her not buying a book, and that would be 3/4, 1 minus 1/4. And we take the probability of her not buying a CD, which would be 3/5, which is 1 minus 2/5, and multiply those two probabilities, 3/4 times 3/5, we get 9/20. And you're right. And that is an alternate way. In fact, that is the demonstration of a law called De Morgan's law, which is involved in both probability and in logic. But the fact is, the reason I did it the long way was to demonstrate the use of those three rules: the rule for or, the rule for and the rule for not. Let's take a look at some applications of probability. I'm a big sports fan, quite frankly, and sports is just a wealthy area to find uses of probability. Some examples are, for example, in baseball. For example, batting average. And by the way, batting average is not an average. It is a probability. It is a probability of a batter at one time at bat of getting a hit. And that's it. And of course, that probability changes as you go through the season. Very few batters maintain a constant batting average. In fact, I would suggest that no batter maintains a constant batting average from the first at-bat to the last at-bat of a season. But it's called batting average, but it is a probability. Also in baseball, we have fielding average, which again is not an average. That is the probability of a fielder fielding a ball and not making an error. 1 minus that is the probability of that player making an error. And winning percentage, which happens to be a probability, which is the probability of a team winning. That is the percentage of the games they've won so far, which most probably should predict the chance of their winning their next game. In basketball, we have numerous percentages which can be looked upon as probabilities, such as field goal percentage, the chance of a shooter making a field goal. Free throw accuracy, which is a percentage and therefore a probability of making a free throw. And three-point shot accuracy, again, a percentage indicating the probability of the player shooting behind the three-point line and sinking the basket. These are all probabilities. In football, passing completion percentage, third down efficiency, and the balance between running and passing plays are measured with percentages. These are all probabilities. And in fact, these probabilities are quite important when you're examining why a team is winning or why a team is losing or how to effectively play against your next opponent. But we're not limited to sports. In fact, a very important area for all of us is the area of insurance. It was mentioned earlier that actuarial science was basically created early in the 20th century to allow for insurance companies to make scientific decisions about what rates to charge and, in fact, who to insure for what and who not to insure. The decision-making process in life and casualty insurance, which is called underwriting, is based on probabilities. For example, let's assume you're buying life insurance. What type of questions is the insurance company interested in about you? Well, the first would be your age. Why? The older you are, the more likely you will unfortunately die sooner than a person who's younger, and therefore they have fewer years to collect their money with a greater probability of your dying sooner, and therefore they charge you more. Your health. And in many cases, if you're old enough or if the amount of insurance is large enough, they may require a physical examination. Because if your health is not very good, then indeed they may charge you a greater premium because the probability of your dying, unfortunately, is higher. Your occupation. I mean, for example, if you work on building skyscrapers in New York City, that's a much greater probability of having a job-related death than, for example, if your job is to play checkers in the window of a department store. You're highly unlikely to fall off your chair and die. So the fact is what you do for a living can influence the cost of insurance due to probability. Whether you smoke or not is another factor that can be used to determine the probability of your death and therefore determine the cost of your insurance. The nature of the structure in which you live, the use of burglar and smoke alarms, the location of the nearest fire station and the nearest fire hydrant are all information used to forecast probability of damage or theft, if you will, at a home or apartment, and therefore homeowners insurance or renters insurance uses these facts to determine probabilities which determine the cost of that insurance. Age, gender, and the type of vehicle and driving record basically determine automobile insurance costs. For a high school or college age male, the one factor in most states that will reduce significantly your automobile insurance premiums is having a B average or higher. Now, indeed, the insurance company could care less about your grades in terms of your being smart or studying or staying home and not driving. They just know from past data that students in high school and college who have B averages or higher are less likely to have a significantly lower probability of having an accident which will cost the company money. And why males? Because female insurance, quite frankly, at that age is not as high. Males have a greater probability of having an accident. Now, driver's education is another thing that will reduce the cost of insurance for that age person. Again, your driver's education simply reduces the probability of a person having an accident. By the way, a third way that a male at that age group can lower his automobile insurance is to get married. But of course, I wouldn't suggest that as a valid reason for marriage. And of course, the reduction in automobile insurance may not be as expensive as even the ring. But that's for you to decide. In fact, when I was 21 and was married and notified my insurance company to put my new wife, on the policy, they not only sent me a congratulatory letter, they sent me a check because my premium was reduced now that I was married. I had a lower chance of having an accident, which would be charged to the company, and they would take a loss. Managers of business use probabilities to determine location of outlets of the retail stores, and in making decisions about new products and designing marketing strategies to improve sales. All this is based on probability. We're dealing with uncertainty. If you knew as a business executive that if you did a certain thing, it would improve sales, guaranteed, you would be probably a genius. Most of those decisions are based on probabilities. Probabilities based on previous experience and available data. The military uses probabilities to predict weapon effectiveness. And in case of war strategies, the number of weapons and the type of weapons that are targeted for a particular location is based on the individual probabilities of those weapons successfully destroying that target. The more protected a target is, the more and the better effective weapons that are placed for targeting on that particular location. Strategies in the military are evaluated for probability. What is the probability of success of a particular strategy? Very important, and when we talk about simulations, we can see how simulations can be used to do that without starting a real war. In meteorology, we talk about the chance of rain. I mentioned that earlier. And every day, if nothing else, which you listen to in the morning news, is the chance of rain that day. Should I take an umbrella or not? The chance of rain, the probability of tornadoes, the probability of particular types of storms are all based on probability. And meteorology uses a great deal of mathematics. So now we've seen a basic introduction to probability. In our next lecture, Lecture 18, we will talk about two specific types of probability, binomial and normal probability.